Well, one thing we can notice is that for this function on this interval, it just so happens to be always increasing. And what we could do is we could take as the x value in each subinterval, we could choose the right endpoint. So if we're doing 4 rectangles and we're using the right endpoint of the subinterval to give us the height of the rectangle, the notation we're going to use is R4. R for right and 4 because 4 rectangles. So I'm going to choose the right x value in each subinterval. I'm going to draw my rectangles using those as the heights. It looks like in this case I'm overestimating all the way, which is fine for now. But let's figure out the approximation of this area. We said that each subinterval is 0.5 wide, so the base of each rectangle is going to be 0.5. The height is determined by the function values as shown here. Now my drawing is not perfect, so I need to be more careful. What are my heights? What are the heights of the rectangles? Well, I have this function f of x, which is given by the formula x squared. The height of this rectangle is whatever 0.5 is when I plug it into this function. So it's going to be 0.5 squared, because that's what my function is. You plug x in, you square it. The second rectangle has a height of whatever you get when you plug 1 into this function. So that's 1 squared. And this height will be 1.5 squared, and this last height will be 2 squared. Again, where did I get these? I plugged the right endpoint of each subinterval into this function. So these are my heights. Now, what about areas? So now the areas of each rectangle are going to be given by taking each height and multiplying by the base. The base is 0.5 in each case because we made each rectangle equally wide. And if we add up all these areas, that's going to give us the right approximation, the right endpoint approximation. So take a moment to work this out and see if you agree with the number I will show you momentarily. So you should have gotten 3.75 in the end once you worked it all out. There's a nicer way to write this formula. If we notice that we have this common factor in each term, which is that common width of the subinterval, we could actually write this formula more nicely. So what we had was this common factor of 0.5, which I'll factor out and I'll put it at the end. And then we had the sums of the endpoints plugged into the function. So 0.5 squared plus 1 squared plus 1.5 squared plus 2 squared. So we could have also written this. This is R4, by the way. We could have also written this using the function notation. We could have written this as f of 0.5 plus f of 1 plus f of 1.5 plus f of 2, all multiplied by 0.5. Okay, so the more general formula is like this. If we have Rn, meaning we cut our area into n subdivisions, the formula will be f of the first thing plus f of the second thing plus and so on plus f of the nth thing, all multiplied by what we call delta x. These things here are the delta x's. Now what if we decided to approximate using the left endpoint of each interval? So L4 would be left endpoint with 4 rectangles again. Alright, so here's our subdivision. So our delta x is still going to be 0.5 in each rectangle. This time we're picking the left endpoint, the leftmost x value in each subinterval. We're plugging that into the function. Now notice in this subinterval, when we plug in 0, which is the right endpoint, we get 0. So we have a rectangle that is completely flat, has no height. So this part here will contribute 0 area to the approximation. In the second subinterval, right here, we're using the left endpoint of this subinterval, and that will give us the height here, which is going to be 0.5 squared, right? Because we plug in the 0.5 into the function. For the third subinterval, again, we're looking at the left endpoint, which is going to give us this height for our rectangle, which is 1 squared. I really should include this one, even though it doesn't contribute anything to the total. And then finally, we have the last subinterval. We pick the leftmost endpoint of that subinterval, which is 1.5. We plug that into the function, and that is the height of this last rectangle. Now notice that the areas of these rectangles are going to underestimate this function. It's not always the case that left underestimates and right overestimates. It's definitely not a general observation to make. In this case, that's what's happening. But remember that functions do all kinds of crazy things. They increase, they decrease. So just keep that in mind. Now remember that we have our delta x, which is the same as it was before, multiplying by each of these to get the areas of the rectangles. And when we add those up, take a moment, try to figure out what this total will be. You should get 1.75. So we know that the area under this curve is somewhere between 1.75 and 3.75, which is what we got for R4. And the reason we know that is because we know that R4 overestimates in this case and L4 underestimates in this case. I keep saying in this case, why? Because left doesn't always underestimate and right does not always overestimate. Now there's one more type of approximation we're going to look at. We're still going to subdivide into 4 equal pieces, but instead of looking at either the left endpoint or the right endpoint of each subinterval, we're going to look at the midpoint, and we're going to use the midpoint of each subinterval as the x value we're going to plug in to get the y value or the function value, which will be the height of our rectangle. And that's going to be called M4. So M4 means we use the midpoint of the subinterval. And the 4 means we're using 4 rectangles. Now once more, our delta x is 0.5 in this example. This time though, we're picking the midpoint of each subinterval as the number we're going to plug in to the function. So this is what it looks like visually, and you can notice sometimes it overestimates, sometimes it underestimates. We don't know if it's doing it exactly right. We don't know what's happening yet exactly. This is just an estimation. So how would I do M4? Well, I'm going to take these heights, but how do I know what these x values are? Well, each subinterval, this is the subinterval 0, 0.5. What's the midpoint of that interval? I'm going to call it x1 bar. It's going to be the average of the left and the right endpoints. So it's 0.25, which makes sense if you look at the picture. 0.25 is exactly halfway between 0 and 0.5. So 0.25 is what I'm going to plug in to my function. And I'll just do one entire rectangle at a time, the area of it. So multiply that by 0.5, which is my delta x. Second rectangle is 0.5, 1. That's my subinterval. What's the midpoint of that? I'm going to call that x2 bar. Again, it's going to be the average of the two endpoints. So you can either do this calculation here, or you can just figure out what is the midpoint of 1 and 0.5. It's just going to be 0.75. So then that contributes a plus 0.75 squared times 0.5 to our area estimate. Next, x3 bar, which is going to be the x value that gives us this height, that's going to be 1.25. We can calculate it the same way as we did the others, but I'm just going to keep this moving. And then finally, the last rectangle, the x value associated with it, we're going to call it x4 bar. That's the midpoint of the interval 1.5, 2, which that endpoint is going to be 1.75. We plug that into the function. Oops, I forgot to square the 1.25 here. Sorry about that. 1.75 squared times 0.5. Now calculate this and see what you get. Now my calculations might not be perfect. You can let me know. I'm not going to re-record this, but I got 2.90625. And that kind of makes sense because it's between L4, which was 1.75, and R4, which was 3.75.